Okay, so yesterday we did 6.1. We are skipping 6.2 because that one kind of comes up in a bunch of different lessons that we're going to do anyway. So real quick, yesterday, just a quick little summary is that we talked about how to identify whether two figures are similar. And if two things are similar, then it means that they are the same shape, but not necessarily the same size. They could be the same size, but they don't have to be. So like one could be like a smaller version of the other, or one could be a larger version of the other. To make sure that that is true, like every single time, what has to be true if two things are similar? Hold on 1 second, sorry. What things have to be true? Colette, what's one thing that has to be true? All the corresponding angles have to be congruent. What's another thing that has to be true? The corresponding sides have to be proportional. All that means in plain English is the sides that match up have to work out to be the same fraction. So like let's say that this is, I'm just making up numbers here, 1, 2, and 3. Then this would be 2, 4, and 6. Because if you set these up in proportions there, you would get, if you did AB over DE, you would get 1/2. If you did BC over EF, you would get 2/4, which is 1/2. And if you did AC over DF, you would get 3/6, which is 1/2. In which case, all the sides are proportional. So when you're checking to see whether things are similar, one thing that you have to do is check to make sure all the angles are congruent and all the sides are proportional. But that's kind of a lie, because while it is true that you have to do that to show that they are, that is a way of showing that they are similar, there's an easier way. So remember that if two things have the exact same shape, then like whether they have or not the same size or not doesn't matter. All we care about is the shape. And what determines the shape of something? The angles. So if the angles are the same, then we're going to get similarity. It's a guarantee that we're going to have it. If all the angles are the same, like the three angles of one triangle match the three angles of another one, we are going to get the same shape. Now, it doesn't tell us anything about the size, but it does tell us about the shape. So today, instead of doing all that work of proving all the angles are congruent and all the sides are proportional, we're going to prove that two triangles are similar only using AA. And what do you think AA stands for? Angle. So angle is a method that we're going to talk about today of proving that two triangles are similar. Now, careful here. This only works for triangles. This is very important that what we are doing today, angle, only works for triangles. No other shapes. It doesn't work for quadrilaterals. It doesn't work for pentagons. Nothing else. This is just for triangles. Okay. So here comes the AA similarity postulate. Remember that when we tried to prove two triangles were congruent and people wanted to say angle, and that was not a thing? The good thing is that when it comes to similarity, AA is a thing. So it says if two angles of one triangle are congruent to two angles of a second triangle, then the two triangles are similar. If you notice in the picture here, angle A is congruent to angle D, and angle B is congruent to angle E. So let's take a minute and think about this. Why is it only 2? Why not 3? Why wouldn't they need 3 to be congruent? Why only 2?
If 2 from both triangles are congruent, then the last one has to.
It has to be. Do you remember what that's called? Third angles theorem. If two angles in one triangle match two angles in the other, it is 100% guarantee that the third one matches the third one. Therefore, if you've got two angles that match, then in a triangle, then you definitely have three angles that match. So you only need to prove that two angles of one triangle match two angles of another triangle, and if you can do that, those two triangles are similar. Now, it's pretty obvious here because, first of all, that they gave us the statement, but I asked you in the homework, and I'm going to ask you multiple times, and this is going to be one of the things that people struggle with, is to make a similarity statement. When you make a similarity statement, it might be with triangles that triangle something is congruent to triangle something. Now, we already made one triangle similarity statement here, but that wasn't the only one we could have made. There might have been another one. Let's talk about how we can, let's pretend that we're not allowed to make this one. Let's say that I need you to make a similarity statement, but you're not allowed to use this one. Even though it's a valid one, we're not allowed to use it. What is another similarity statement we can make?
You could say triangle BCA is equal to triangle EFT.
Good. Notice that she started here, B, C, A. So she went like that. I didn't care what she said for the first one, but as soon as she said the first one, I already knew what she should be saying for the second. Now, you might be thinking she started in the lower right-hand corner and went to the lower left-hand corner and up. And that really wouldn't be such a great idea of a method to use because if one of these triangles were rotated, then it would be a hot mess. But hers matches anyway. Notice that she started from the one that had two angles. So we're going to start from the two lines on that angle. It has two lines on that angle right there. Then she went to the one that has three lines. So there's our second destination there. And then we ended up on the one that has one line. So it's that same exact pattern. In this case, they're oriented the same way. So EFD would definitely be the way that they match up. Please make sure that you write that they are similar. They are not congruent. They are similar. Same shape, not necessarily the same size. Sorry, my writing hasn't shown up there yet. Hopefully that'll pop up on the screen in a second. It's a little behind. So there's lots of different similarity statements that we can make, but it really depends on what the first three letters are. Once the first three letters have been declared, then the second three definitely matter. So it's not just whatever you want. The first one could be whatever you want, but once the first one has been determined, the second one, it has to be a certain way. Are we okay with that? Okay, this is called the AA similarity postulate. Remember that because this is coming back in a few slides. All right. Let's tell whether the triangles are similar or not. Now remember, we've only got two ways at this point of determining whether two triangles are congruent. Now, if you notice, there are two triangles in this picture. Talk to me about them in plain English. Where are the two triangles? Colette.
You have the big triangle, and then
I'm going to use two colors here. Let's use red is the big triangle. Where's the second one?
the second one is right. You see it in the first line on the top.
Here? There's our second one right there. So when we're talking about which triangles are congruent, we're talking about those two. I'm sorry, not congruent. Whether they're similar or not, we're talking about those two. So we have only got two ways that we can do this. Number one is we can prove that every angle in the blue triangle matches every angle in the red triangle, and every side of the blue triangle is proportional to every side of the red triangle. Or, that's one method. The other method is that we could use the AA similarity postulate. So if these are going to be able to be proved similar, then we're going to have to use the AA similarity postulate. What do you got?
I know how to find one of the angles.
Okay.
Since they're parallel, you know, those.
Okay, that's very important information.
Then the line crossing through the parallels?
The one on the left or the one on the right?
The one on the right.
Okay, here's a line that is crossing through two parallel lines.
Is it transversal? So, like the angle of the smaller triangle is a corresponding angle of
Which angle? Just give me a direct. You don't have to be too specific, but when you're saying the angle, the bottom, which one?
bottom right of the smaller.
Okay, bottom right of smaller. Okay, keep going.
Is a corresponding angle of the larger right, bottom right of the larger one.
Good. So here's what he said. He goes, I see those two parallel lines there. That line on the right is a transversal going through them. So since the lines are parallel, I know I know that because of the corresponding angles postulate that these two things must be congruent. But that is not going to be enough to say they're similar.
The like the top angle, since the red triangle and the blue triangle are overlapping, that the top angle is the same angle for both.
Good. Notice that this angle up here is the top angle of the blue triangle. It also happens to be the exact same angle that is the top angle of the red triangle. Now, some of you were probably not even noticing that. Was there somebody going to go for something else? Like, was there something? Yeah. So what were you going to go for instead?
The other side.
The other side, we could have gone for corresponding angles as well. But we don't need to here. We know that top angle is congruent to the top angle. That lower right-hand angle is congruent to the lower right-hand angle. So when it says, determine whether the triangles are similar, Yes, they are similar. And what's my reason for why they're similar? The AA similarity postulate, or just AA? Some of these will be easier to see than others. Let's go to B.
They are similar because the two angles are the same.
Yeah, I mean, this one kind of stands out. Like we've got this angle matching this angle, and this one matching this one. So yes, we got the AA postulate again. Question, Colette? Did you want to take the next one? Okay.
I'm saying that this one isn't similar. It's congruent because the same.
Okay, so she's saying that actually, in fact, these two things are congruent because of SAS. Well, talk to me about that, and then I'm going to come back at you in a minute here.
So the line in the middle is going to mix itself. And then we already have the line on the outskirts of it.
Okay, so
We already have the angle. We already know that those angles are congruent to each other.
so she's saying the triangle on the left and the triangle on the right are congruent by SAS, but that's not what they asked, actually. They actually asked, are they similar? Well, we got to back it up. Like, I mean, that's all. Like, I don't mind whatever we say. I'll go along with whatever. I just want to hear why.
No, because similar triangles can't be congruent.
Okay, have I ever said that?
Well, like,
What is the words that I use when I say when two things are similar, they're what?
their sides are, their angles are congruent and their sides are proportional, so they can't be like exactly the same.
I said they can't be exactly the same?
They just proportional means not exactly the same.
I always say similar mean, like when I say congruent, I say congruent means same shape, same size. What do I say when I say similar?
Same angle.
Not necessarily. So when I say, I don't say not, I said not necessarily. So here's the thing. First of all, congruent triangles are always similar because they meet that definition. First of all, when two triangles are congruent, we know that they're going to have the same angles. So, but actually, I can do this without using congruent things. Talk to me about this for a moment. I'm going to actually ignore what Colette did, even though her way is so good. She said they're congruent. Well, if they're congruent, it's a guarantee that they're similar. But I'm not like, right then I go like, well, why are they similar? Because they're congruent, so therefore, since they're congruent, they have to be similar. I can use these two lines right here to tell me something pretty magical about this triangle right here. Amber, what do you got?
It's a perpendicular bisector because we know from the because since the conversation perpendicular bisector theorem says that the sides are going to be equidistant from the.
You're not wrong. So here's what she's saying. She's saying that since this point here is equidistant from the ends, then this must be a perpendicular bisector. She's not wrong. That's not what I'm using to prove that these are similar, though.
The two angles on the sides are the same angles.
When you say the sides, give me an idea. Give me a direction, like where?
The right and the left.
Right here? This one?
Yeah.
Why are those two things congruent to each other?
Because it's equidistant, they're the same length, so like when they meet, they're the same angle.
This is, whatever way you're describing it, I think is maybe not the right reason for it, but you're not wrong about that those two angles are congruent. Yes, ma'am.
So maybe by the hinge theorem, you can conclude that since the two sides are the same length, then the two angles would also be the same. Like the one with the red line in the middle and the blue baseline.
So I want to go as far as to say I can do it with only this. Like, forget about this. I'm not using this. I'm not using this angle. I'm not using any of that. All I'm using are those two blue lines to determine that those two angles are congruent. How am I doing that? The only thing I'm looking at, I'll tell you, I'm not using any other information in this picture other than it's a triangle, and I see these to give me this piece of information. How did I do that? What about an isosceles triangle?
That because the two legs are congruent, the angles are also congruent.
Base angles theorem says that if this is an isosceles triangle, so none of these reasons have been wrong so far of why these are, but But right there, it gave me that piece of information that this is an isosceles triangle. Therefore, those two things are going to be congruent. That's why I like that. I go, oh, okay. So now what I can do is I can say, oh, these are definitely congruent by, these two triangles are definitely similar by AA. Because I used the base angles theorem to show that those angles were congruent. Now, it would also be okay to say that the triangles are congruent, and then use CPCTC, and then say that those angles were congruent, and then from there go to get angle. It just seemed like a longer path for me. Yes, ma'am?
Can't you also say that because it's a perpendicular bisector that the two angles?
It doesn't. A perpendicular bisector doesn't tell us about the angles. Here's what it would give us. A perpendicular bisector would give us, if I know that this line is a perpendicular bisector, I know this angle, and I know this angle. And actually, that would help me.
Yeah, that's what I was
That's the other angle. Okay. That could be a second angle that I could use. But it wouldn't tell me anything about the angle in the lower left and the lower right. So all of these have been very good ways that we can use for angle. Let's talk D. Now, where are the two triangles? Let's define where these two triangles are, first of all. Like, where are the two triangles we're talking about? Okay, so here's one of the triangles we're referring to. And where's the other one? This one over here? Okay, good, because that's not a triangle over there. Just be careful because it's easy to just be like that thing. So those are the two triangles that we are trying to compare. Let's talk about them. Colette, what do you got?
I would say that there's just not enough information
Okay.
to tell us that it's similar.
Anyone think anything different?
They both share the angle on the bottom left.
Bottom left. So notice of the tinier triangle, the smaller one, there is an angle right there. I don't know what that angle is. It's just an angle. That angle happens to be the exact same angle of the big triangle as well. It doesn't change size. It's the lower left-hand corner of the big triangle. It's the lower left-hand corner of the small triangle. So it's definitely going to be congruent. So these will definitely be by AA. I could even make up a scenario. Why are those two triangles similar? Amber, what do you got?
Because since the triangle is 180 degrees, we know that one angle is 90 degrees. And then we also know that if that angle is 30, then the other angle has to be 60. So then...
So we have to be careful because sometimes things don't look like the angles match up at first, but in fact they might. We go, oh, wait a minute. It's not that 60 and 30 match each other. It's 60 and that invisible angle, the one we hadn't seen yet, the one that we weren't sure about until we did that calculation to say why these are similar. That's what we're looking at there. All right. So if we can prove that two triangles are similar, then we know that all their angles are congruent, and we know all their sides are proportional. You must be very careful with this. Because when you compare two things, you have to make sure you are comparing the corresponding pieces of a triangle. Meaning, like, if you're saying, well, I'm going to use this number of this triangle and this number of the other triangle, you better be sure that both those numbers match up. So, before you do anything here, like if you're about to do anything, if in your little brain you're going, hey, I'm about to do something using similarity, then you better prove to me that these are similar first, or I will give you no credit for this question. Yes, ma'am?
The two triangles are the big ones.
Okay, so the largest one, which we see here, I'm just going to outline them just in case you can't see it. Here is the largest triangle. Where's the other triangle?
The one on top of the one that you're
Okay, so those are the two that we're looking at there. So when we compare things, that's what we're looking at. But when we still don't know whether they're similar or not.
Since the top line and the bottom line are parallel,
the long line is being a transversal.
This one over here?
Yeah.
Okay, so we're using that as a transversal.
And then the top angle of the bottom right angle of the top triangle should be to the bottom right of the,
What reason is that?
corresponding angles.
Yeah, the corresponding angles possible. Two lines are parallel, and their corresponding angles are congruent. Okay, we have an angle. Go ahead, Amber. Go ahead.
The top angle they both share, so it's automatically.
Okay, that's the top angle of the blue triangle. It's also the top angle of the red triangle. So right now, we have angle, angle. You have proven to me that these are similar. Now you can start doing stuff because whatever you want to do is okay as long as we follow that. Yes, ma'am? Okay, so we're going to find a scale factor.
And so, you have to find the total amount for the left side of the big triangle.
Okay, so she wants the left, she's talking about the big triangle here. She's saying, let's figure out what the total left-hand side is. She says that is the left-hand side of there. It's not just 3, it's not just 1, it's 3 plus 1, which is 4.
And then, what do you put the length of the smaller triangle and then 3.
The length of the left-hand side of the small triangle is just 3. What is this number, 4/3? What is it? Why is that number important? What is it?
It's like
Wh-
every 4 minutes.
What did we call that number? It has a name. It starts with an S. The scale factor. So, since we put big on top, it means that the big one is 4/3 the size of the small one. So, just as a note, just because it's not asking it here, but just so you know what that number is, in case you have to do it on a different one, this is the scale factor right there of one triangle to the other. Okay, so 4/3. That's an important number.
So now we solve for x, and basically it would be set up as x over 5. It would be 5 plus x over 5.
Okay, so she's taking a look at this side right here. And she's saying, how long is that side? It is not x, it is not 5, it is 5 plus x. Isn't that what you just said? You said 5 plus x.
Yeah,
You're not wrong.
5 plus x over 5, and then it's equal to 4 thirds.
Why is it over 5, Colette?
Because that's the length of the small triangle.
The length of the big triangle, its right-hand side, that diagonal there, is 5 plus x. The length of that same diagonal in the blue triangle is just 5.
So now I have to solve and
Okay, so we're going to cross multiply, and we get 3 times 5 plus x. Now, I put that parentheses up there. It wasn't there, but that's because if I don't put it, sometimes people just multiply the 3 with the 5. It's got to be multiplied with both of those things. Over here, we've got 4 times 5.
so it would be 15 plus 3x is equal to 0. And then you subtract 15 on both sides. And you get 3x is equal to 5. And then you divide that by 3 on each side. Your x is equal to 5/3. And if you simplify it, can we simplify it?
Well, I mean, it can't be reduced. You could turn it into a decimal, but the truth is that I don't know that we really want to.
No, like, could we do it the next number?
Oh, you could turn it into a mixed number. Now, here's what I say is I go, I don't mind if you leave it as an improper fraction. You do run the risk when you convert it. So let's say that you decide to turn this into a mixed number. I'm not against that, and I don't want this to turn you away. But understand that if you do a conversion here and it doesn't match up with what actually this is, it could leave you as a problem. That's why I say, why risk it? Just leave it as 5/3. But let's go ahead and do that anyway. Let's figure out what 5/3 is as a mixed number. That goes in once, 1, and 2/3.
the length of X.
Perfect. Let's say that I asked you how long, I'm going to give this some letters for a minute here. I need some letters so that when I do this that you guys know what I'm talking about. If I asked you how long BC is, how long would you tell me BC is? So what is BC? 6 2/3. So we got to take a look at that and go, yeah, it only asked me for X, but what if I asked you for BC? In which case it's 5 plus 1 2/3, which would be 6 2/3. Okay. Let's talk. Before we can start answering these questions, the very first question says, triangle ABC is similar to triangle blank. Before you start doing anything, you better be sure that these are similar, because I would have no problem giving you a question like this and not making them similar and watch you do all the work to find out afterward that they were never similar. So let's just talk about this. Let's determine whether they are in fact similar. Somebody different. Give me somebody new. Okay, so we're talking about the big triangle here, and what other triangle?
And then at the top with the first line of the triangle. So this is parallel, and we can use the right side as a transversal.
Okay, so this line right here, I think he's talking. Oh, there we go. Well, now that we have letters, give me some letters. Angle what and angle what?
Angle A and angle E are congruent to the corresponding.
Angle A is totally okay. I don't know what angle E is. Sorry, angle E doesn't make sense. It does not compute. That'd be the wrong name for any angle right there. A is totally okay. E is not.
DEB.
DEB is a great name for it. Because here's why, just in case, if sometimes people go like, why do we have to keep doing that? Because I don't know whether you're talking about this angle or that angle. So we have to be very clear there as to which one we're talking about when we say angle E. Okay, we got one angle.
And then add DBE as an angle, and then shared.
Okay, DBE is a shared angle between the two. So now we know that these are in fact congruent by the AA similarity postulate. I'm sorry, yes, I say congruent. I get so used to saying congruent all year round, and then we switch over to similarity. Thank you for correcting me. Okay, so they gave me the first part. I don't get to choose anymore. I don't have that free choice. I have to follow their pattern. Yes, ma'am?
Triangle EBD.
Good. So they went from A, so like from the one that had one line, down to the one that had two lines, and then over to the one that had no lines, A, B, C. So we're going to do the same exact pattern, go from one line down to two lines over to nothing. So that would be EBD. So triangle EBD. The similarity statement is actually one of the most commonly missed questions just because people go too quickly on it. It's like a quick question. They go, oh, yep, blah, 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 that's it, no problem. It's commonly like one of the places where people lose little points left and right. Okay, so let's talk y now. We need y. I don't know anything about math. I guess you're going to have to help me with this. I'm not going to lie. I faked geometry all the way up to this point, and it turns out that I don't know anything more. That's it. Yes, ma'am. Okay, let's find the scale factor. How do we find the scale factor?
We have to find sides that we know. So
Good.
we could use, we know the big triangle, the base, CB is 3 plus 4.
So just so you know what we're talking about, CB is 3 plus 4, which is 7.
And then we know the little triangle is DB, which is 4.
Which matches up with the little one, which is 4. So DB is 4.
And then you could put big over small, so 7 over 4.
By the way, it should be okay putting small over big as well. It doesn't matter as long as we follow that. Like, we have to follow whatever she did. So just as a reference, in case you get stuck, I'm going to write it just like she said it. Big over small, which is totally okay. It reminds me which goes on top, which goes on bottom.
Okay, and then that's
Okay?
So then we just have to find, we have to find y, so that would be 8 over y,
Good.
and then we would, cross multiply, which would be 32 equals 7y, and then you would divide, and that gives you.
This is usually during test time where somebody freaks out because they're like, 7 doesn't go evenly into 32. Who cares? Nothing in this world seems to go evenly into each other. Like, it's just whatever. They end up as numbers. Don't sweat it.
4 times, which is 28. And then, why don't I ever do that? And that's it, 4 over 7, or 4 over 7, right?
Yep, 4 and 4/7. So why is 4 and 4/7? I realize that's not a pretty number, but it is what it is.
We can leave it as an improper fraction, right?
As 32/7? Yeah, you can leave it as 32/7. Whatever you want, because here's the thing, is that if I end up having to multiply or divide or add or subtract, sometimes improper fractions are a little bit easier to work with. The next one is saying BE over BA is equal to what? I'm going to move some of this stuff here. Let's see if I can just move this. Oh, no, that just copied it. Okay, I'll just write in here. So BE over BA. So we just need to plug in those things. What is BE over BA?
Just 3 over x.
Okay, so 3 over x. Okay. And no?
3 over 3.
Good. We have to be very careful with that. So we've got the right-hand side of this triangle is 3. The right-hand side of the big triangle is however much this is. So it's 3 plus x. So we have to be careful with our denominator there. Our denominator is not x, it's 3 plus x. It's x plus that 3. Last thing we need to do is figure out what x is. Yes, sir.
Okay, so since he used big over small, we would use 7 over 4 equals 3x over x. Oh, 3 plus x. Sorry.
Good. 3x and 3 plus x are not the same thing, just to be clear. One is 3 times x, one is 3 plus x. So 3 plus x over x. Okie doke. So we've got 7 times x is equal to 4 times 3 plus x.
Then you get 7x equals 4 plus 4x.
Okay, keep going.
Then take the 4, subtract it, and then put on the side. And then divide 3.
What do we end up with?
4.
Beautiful. Yes, sir.
Why do we put it over x and not over 3?
So, good question. Why did we do x and not 3? Like, why did we do, like, here's what he's saying. He goes, we did 3 plus x as the right-hand side of the red triangle. Why did we use x for the right-hand side of the other triangle?
Because 3 and x make up the big side of the triangle.
Right, but I think what he's saying is this, is he agrees with you that 3 plus x is the right-hand side of the big triangle. What is the right-hand side of the little triangle? Not x. It's okay. These are the things that we do, right? Like, these are the things that we check. So we go, you're right, that was a good call. This should have been 3. So guess what? Unfortunately, all this goes to the wayside here, and we'll go, let's try this again. That's good, though. Like, we need to be able to catch those things and go, all right, something happened. We would have only made it about 10 more seconds before I go, okay, so why did this go wrong? So 3 times 7 is 21 is equal to 12 plus 4x. I think that's where we left off.
Yes, and then you subtract x from both sides.
Let me just check my numbers there. I did that really quick in my head. 3 times 7 is 21, 12, 4x. Okay, I'm sorry. Subtract what?
12 off both sides.
Okay, and what do I get?
9 is equal to 4x. And then you divide by 4 to both sides, and then that gives you 2 1/4.
Okay, 9/4, 2 1/4. But at least we know that x is right now a number that it wasn't as easy as just 4. That would have been nice if it was 4. But unfortunately, it was 9/4 instead. And I know what you guys are thinking. You guys are thinking, you know what I really miss is something that we haven't done in a Bum, bum, bum. What? Well, if we have proofs here, be prepared for proofs. I know. I could see everyone's joy coming out. Colette, you want to help me out?
So first you have to set up the proof. So if you statement and then reasons. And then you write your given and your statement on something. AC is parallel is given. And then you can start off giving your thing is similar. So we know that so what we can say is angle.
Pause for just a minute. I want to focus on what you just said because I love it. Is that what we're doing is we're trying to prove that they're similar. So keep that in mind. We have ways of proving that they're similar. That should be in your head. How am I going to get there? Okay, go keep going.
So now we can say that
Angle DOB, this one right there, angle DOB,
is congruent to angle AOC
angle AOC, that's this one right here.
because they're vertical angles. And then we can say that what's it called? Angle angle ODB is congruent to angle ACO because they are alternate interior angles. And then we don't have to go any further. Well, now we can say that,
Let me ask you a question. Is it okay that she said that those two angles, that like she just said they're congruent and used alternate interior angles? Sorry, I'll add on theorem there. Is that okay? Is she allowed to do that? Why? She is. Why is she allowed to do that? Because a lot of times yes, exactly. Because they are parallel. A lot of times you guys used to say this to me all the time in when we were doing proofs, and I would stop you and be like, you can't say that. And you'd be like, why? And I'd be like, because you haven't proven they're parallel. But we already know they're parallel, so that's totally okay. They are parallel, therefore, we can say that these are congruent by the alternate interior angles theorem. Sorry, I didn't mean to cut you off, but that was a good line.
so now we can say that triangle AOC is similar to triangle BOD because of AA.
AA similarity postulate, you can write AA and I'd be okay with that. Now here's what I would not be okay with. I'll tell you where I would be a huge jerk. I'm going to write something here. Do not copy what I'm writing. Do not write this. If you wrote that congruent, then you just missed that entire line there. Because not only are they not, do we not have enough information to prove that they are congruent, we cannot say AA and call them congruent. So don't say they're congruent. They're similar. Two totally different things. Now, two similar triangles could be congruent, but it doesn't mean that. Okie dokie. Yes, ma'am.
Just to be clear, if a triangle is congruent, this is similar.
Yes, every single set of congruent triangles are also similar. Not every set of similar triangles are congruent. Alrighty.